We'll mute ourselves because she's online.
Let's wait for me to sit on. It doesn't feel Great. Well, hi everyone. Welcome to our 11th Kavli lecture. And thanks very much for all of you for coming. So it's my pleasure to introduce, at least online, Vicky Kalogera today. So she's the Daniel I. Linzer Distinguished University Professor of Physics and Astrophysics at Northwestern University, where she's also the director of the Center of Interdisciplinary Exploration and Research in Astrophysics. A mouthful. So Vicky's made major contributions to the astrophysics of compact binary objects, and particularly to their X-ray, radio, and gravitational wave emissions. And that's going to be the subject of her talk today, so we're very much looking forward to hearing what she has to say. Her work's been recognised with many awards, honours and prizes, and let me just highlight a couple. So in 2018, she was the recipient of the Danny Heinemann Prize in Astrophysics, and in the same year, was elected a member of the National Academy of Sciences. So as you can see, sadly, Vicky's not with us today, basically due to a number of travel commitments. But I'm delighted to say that she has promised that in September, when she's visiting the UK for a LIGO Virgo collaboration meeting, she's going to stop by. So we'll have a chance to speak to her in person then, to thank her properly for her lecture. So as I said, today Vicky is going to tell us about gravitational astrophysics, gravitational wave astrophysics, progress and puzzles, and we're very much looking forward to hearing what you have to say, Vicky. So whenever you're ready.
Thank you for the introduction, and also thank you for tolerating this mixed presentation mode, but also split visit setup. So I had the pleasure of meeting some of your students just before the lecture. I'll do the presentation today, but also, as Anthony said, I will be visiting the UK for an extended period of time in mid-September. And I will definitely come and visit and see you in person, spend some time. I'm looking forward to seeing you and talking with you more in person. So I don't have access to the chat while I'm talking, but please, if you want to ask questions along the way, don't hesitate. So I hope somebody can be looking at the chat, or just raise your voice and interrupt me as if I'm in the room, and then I'll be happy to answer questions along the way. Don't wait for the end of the talk. All right, so let's get started. I will, my plan for today, and hopefully I will stick to the timeline as well, is to give you an update of where we stand when it comes to the LIGO Virgo discoveries. I will not be able to cover everything, of course, but I will focus mainly on binary black hole discoveries, and I will summarize some of the results from the collaboration, but also I will highlight some of the work that's being done in my group outside the collaboration when it comes to astrophysical interpretation. But of course, getting started, let me see. Right now I'm not getting, oh, there it is. I have to make sure I give credit to the hundreds and hundreds of people and dozens of institutions that have made this possible while working over decades. I joined the collaboration, it's scary to think, but over 20 years ago as a postdoc, It was a scary and risky move at the time. And back then, and still now, I'm only a part-time member of the collaboration. As I was told back then, astronomers were not very supportive of joining this collaboration, and I learned to not do my full-time research work on gravitational waves, and I haven't changed my mode since then. You can see, of course, a number of institutions from the UK are part of the LIGO scientific collaboration. Now, within my group, when I joined, my focus was exclusively astrophysics, source modeling, making predictions for detections. And I'm sorry, can you hear the beeping from my own laptop? I would like to fix this, so give me 1 minute. I'm gonna do this quickly. Okay, let's go back on it. Okay, hopefully we'll be good now. There. But about 5 years in the mid 2000s, I basically got intrigued by data analysis. And by now I consider myself not just a theoretical astrophysicist, but also a gravitational wave observer. With Alberto Vecchio from the University of Birmingham, we started a collaboration and basically developed we were the first two groups to develop all the methodology and tools within the collaboration so that we can do astrophysics parameter estimation. So up until that point, everybody was working on either the instrument, detector characterization, or making sure we're not going to lose the signal if the signal is in the data. And believe it or not, people were not thinking about, once we find the signal, what are we going to learn about astrophysics? So Alberto and I spent several years doing what at the time was considered work in the periphery, and actually figuring out how we're going to learn about the compact objects we are detecting and their mergers. And by the time we got to the point of doing test injections, we convinced the whole collaboration that yes, that is actually important, because what else are you going to say in the papers if you're going to announce a discovery? So astrophysics parameter estimation, how are you going to extract population properties, how are you going to do model selection is something that my group has focused for a big part in the last several years. And then, but along the way, I got interested in the instrument, and actually with collaboration, interdisciplinary collaboration with computer scientists, I've had a lot of fun learning more about the instrument and the noise, and focusing on the noise and not just the detections. So if you want to play with the noise yourself, you can look up a citizen science project that we developed called Gravity Spy, and help us classify noise so we can clean our data and couple classifications by humans with machine learning so that we have cleaner data and we can dig deeper into the noise. Okay, so with this overview, let me now move into where we are at present. So right now, the detectors are not operating. Some of you may know. All our detectors, LIGO, Virgo, are undergoing major upgrades as we are preparing for what we call O4. This is our 4th observing run in the era of advanced LIGO. Kagra is the Japanese detector that is also is going through an upgrade, but preparing to have a science run, their 2nd science run in conjunction with LIGO Virgo. And then LIGO in India is in construction. or preparing for construction, depending on how you view it. And hopefully we will eventually have a 4 detector network into the future. What the data and the discoveries I will be summarizing today are basically the full data set we have from the 3 observing runs. And the 3rd observing run was basically split in 2 parts. It was affected by the pandemic. Our analysis, the run itself, our analysis and dissemination of the data was affected by the pandemic. And these are the days that we were covering. So I'm going to focus on binary black holes. And at this stage, we actually are dealing with a sample, a firm sample of strong detections of 90 mergers of black holes and neutron stars. The majority of them are binary black holes, but we do have 2 double neutron star detections, one, the famous multi-messenger detection, and 2 neutron star black hole detections. The rest are all binary black holes. This is just a visual of how the gravitational wave chirps of all these 90 sources look like. This is our very first one that looks probably maybe not the best, but one of the best of these banana-shaped frequency time plots, where you can see the chirp signature frequency is going up as a function of time, and the signal is becoming stronger and stronger. But you can see that depending on the signal to noise ratio, not everything looks as clean and beautiful as the few strong sources. What I care about a lot, and many of the astrophysicists or gravitational wave astrophysicists care a lot about, is the masses. So here's a summary plot that we use in talks. It doesn't include error bars, but of course we care about the error bars. So just for a visual impression, I'm showing you here all the gravitational wave detections on a y-axis that shows the individual masses of the black holes. And the x-axis is nothing, it's just an ordering axis. The blue dots are all the LIGO Virgo. Now the Kagra collaboration also works with us, even though has not contributed into detections. So it's the gravitational wave mergers. And each one of these sources involves, of course, 3 black holes, 2 merging into the final merger. So each source has 3 dots. We used to have them separately coming together, but now we have so many sources, we're putting all in one line, and it's harder to actually include the error bars. We used to have a plot with error bars as well. Along these lines, on the same plot, we're also showing black hole masses and neutron star masses as measured through electromagnetic observations in the 2 different colors. And here you can see already visually that black hole masses from gravitational waves extend to higher masses, as you may have heard from many talks of this type. But it doesn't mean that they're completely separate. We have an overlap between the low mass black holes that we observe with LIGO and the mass measurements that we have from electromagnetic observations. So apart from masses, there is a number of other things that we extract from the gravitational wave signals. We measure rather, not always rather well, I should say, but we can measure and quantify the error bars, masses of the black holes. We can constrain spins. Sometimes I don't always call it a measurement. We can constrain spins of black holes. We can measure the luminosity distance of the source, since the gravitational wave measurement is a measurement of amplitude instead of the energy of the source. And also we can measure rather well event rates. I'll spend a little bit more time on this and their significance. And the reason we can measure event rates quite well is because we we can quantify selection effects, both associated with our detector, but also with our detection methods. We can quantify selection effects quite accurately. So it's a well controlled experiment, and therefore selection effects are, well, not easy, but compared to other astronomy experiments, easy to quantify. The kinds of questions that we are overall interested in addressing is features in the mass distribution. I'll spend some time on these, especially the black hole mass distribution, because we have a dynamic range for black hole masses. Especially we expect astrophysically that maybe there should be an upper black hole mass gap. Would like to understand if the gap exists, what is its origin. There's also electromagnetic expectations that maybe there is a low mass black hole gap. Maybe it's connected to the maximum neutron star mass and equation of state questions, also noted down here. Would like to understand from the observations directly, what are the astrophysical merger rates for all the classes of our mergers? And is there a redshift evolution? Is there cosmological evolution? How does it compare to star formation rate and its redshift evolution? If there are, would like to be able, hopefully, to extract potential physical correlation between source properties, that maybe we can find the signatures of these correlations directly in the data. If we find weird systems, outliers, what do they imply? Are they telling us something about exceptional formation paths or something else about properties of compact objects? And of course, the big umbrella question is, how are these systems formed? So the question of origins is at the center of all of the analysis we pursue, either inside the collaboration or outside the collaboration. So on this big umbrella question of specifically binary black hole formation, there is two types of formation channels, two big categories of formation channels that we tend to consider. One category is involving isolated binaries. So zero-age main sequence stars in an isolated binary, they can go through their evolution, and some of them can stay bound throughout the evolution and form binary black holes that eventually may merge within a Hubble time. We consider them across metallicities. Rotation may or may not play a role in a dominant or non-dominant way. So there's a lot of work down that path. Another big category for binary black hole formation involves dense stellar environments or dense black hole environments. And those environments can be found in different contexts. So globular clusters, old, young clusters, galactic centers with or without AGN disks having an influence, but also primordial black holes and dynamics playing a role there in terms of forming binary black holes. So in this big picture context, we use a lot of the work that happens inside the collaboration is as model removed as possible, in the sense that we try to focus only on the data and look for data-driven signatures that might then point towards characteristics that might be uniquely associated with one formation path or another formation path, etc. We never in the collaboration adopt a very specific astrophysical model with its parameters and its messiness and make a direct comparison with the data. So this is something that is decided in terms of a sort of principle, and all the detailed model comparisons are done by individual groups independently. Okay, so in this talk, I will try to touch upon these 4 topics, and then we'll see how time is gonna allow us to do that. I'm gonna start with a few key points about merger rates and their measurements. I'm gonna be starting usually from the measurements. Masses will be the next topic, spins, the 3rd topic, and then depending on the time, I may tell you about some surprises and how they don't fit the picture, okay? All right, so let me get started with rates. Now, before I dive into rates, maybe I'll pause a little bit. Are there any questions you'd like to ask right now? Okay, so let's get going. I'd like to make a point before I give you the big picture about rates and how they may or may not be used to draw conclusions. I'd like to make a point that often is lost in terms of a difference between electromagnetic and gravitational wave astronomy. We were able to make rate statements all the way back to when we had a single.
Vicky?
Yes?
Yes, we do have a question, actually.
Okay.
Yeah, I wanted to ask about completeness, because there have been some claims that of inefficiency in the detection pipelines. And this
Yes.
is what and so that, and since you're going to go on to event rates, I wanted to know what your thoughts were about that.
Yes, yes. So of course we make our data available once we do our basic analysis, and we make our data available, we make our codes available, but independent groups can analyze them. By the way, we run workshops for people to learn how to analyze our data, etc. We had a workshop run this week, and group members of mine were giving lectures, etc. And there is one very strong group at the Institute led by Matthias Aldarjaga, who have been successful in finding more events than ours. And that's great. And I can comment on the following. They recover all the sources we are finding, but they are digging more into the noise. And we have worked with them to understand what's going on. And I can tell you that basically they are a lot more aggressive or risky in terms of tolerating less confident detections, okay? So their pipelines, and also, I should say, they are doing a different, they are using a different way of calculating the power spectral noise curve. So if you're calculating your noise somewhat different, then of course, your signal to noise calculation is different, slightly different, etc. It's not hugely different. So they are able to find more events down in the noise. When we use some of their assumptions, we find the same events. So there is no inconsistency or magic or whatever, but we have decided in the collaboration, you know, whether individuals agree or not agree, it's a team effort and it's a team decision to not go down that path and be, as a collaboration, more conservative and stay on the conservative side. So that we are absolutely firm that our detections have a high astrophysical confidence. But of course, we're very happy that others are finding more events, and the population conclusions are actually not affected by these low signal to noise ratio additional detections. Does this address your question?
Thank you.
Yeah, thanks, Vicky.
Thank you. All right, so now we're jumping into rates. So we made rate statements all the way back to an event. My group calculated this, and you can laugh, I laugh. But remember from the binary pulsar experience, we had 2 double neutron stars for a long, long time that would merge in a Hubble time. And we were using those 2 systems to calculate rates with a lot of assessment of the systematics and make predictions for LIGO. And those rates were uncertain for those 2 double neutron stars at the time were uncertain by 3 to 4 orders of magnitude. Now, so we get one event and we make rate predictions. How can you do this? I also, my brain is telling me you should accelerate, Vicky, and not tell a long story, but how do we do this? We do this because we can quantify the selection effects really well. And through our simulated injection analysis. But of course, with one event, we have a broad range. So uncertainty factor of a couple of orders of magnitude. The point I would like to make is that as we increased our number of events, and here it's only 10, this is at the end of our second observing run, the constraint of the range narrowed, so uncertainty of factor of F5, but it didn't shift from the original broader range. So, and that is a testament to the fact that we have a good understanding of our selection effects and detection pipelines and understanding of how our detector works and our data analysis work. And this has persisted basically through our analysis. Now, there is another thing to point out, the difference with electromagnetic astronomy, is that the improvement in our rates is not just Poisson, okay? It's not just the square root of n, we have more systems, we can constrain the rate better. Why? Because the basic parameter we measure in gravitational waves is mass. But the luminosity of a gravitational wave source is mass dependent. And you know that in order to calculate a rate in astronomy, you need to know something about your luminosity function. So because of our good selection effect modeling and the fact that with every source, we measure the masses, we're basically constraining our luminosity function better and better. And therefore, we don't just have an increasing sample, but we also have a better constraint on our luminosity function. In electromagnetic astronomy, you don't know the absolute luminosity function, okay? You know flux distributions, but you don't know the absolute luminosity function. We measure masses, we're constraining the absolute luminosity function of our population. So our rate calculations is actually improving faster than the Poisson factor. And now with, in our population analysis, by the way, we don't even use the 90 systems or the 85 systems, we use only 75, even more conservative. Our rate uncertainty right now has gone down to 2.5. For binary black holes, this is huge because the theoretical predictions were uncertain by 5 orders of magnitude. And within basically 5 years, we know the binary black hole merger rate to within a factor of 2 or 3. Okay, so we're gonna keep this thought in our minds because from time to time, we'll be talking about rate constraints against models from 2 or 3 events. Okay, so that's why I'm making this point. All right, now let's, I'm gonna show you some busy plots, but making a rather simple point for each one of them. These are summary plots of what? Of rate predictions, in this case for binary black holes, from many theoretical studies using different formation paths for binary black holes. And the predictions are for the local binary black hole merger rate density. And the bars, because many of the predictions are not really, value plus or minus an error, it's ranges, etc. So the bars show you the ranges that have been predicted. And you see isolated binary evolution, POP3 stars, globular clusters, nuclear star clusters, primordial, etc. The vertical band is our current tight prediction, tight measurement of the binary black hole rate. And basically, you can see that given the uncertainties in the models, you can say that some channels are rate challenged, I call them, but you can't really use the rate to exclude any of them. Okay, you can say that isolated binary evolution maybe over predicts typically, and dynamics under predicts typically, but the measurements are giving us a really tight constraints on the model on the models right now. But we're not excluding anything based on rates right now. So that's the punchline here. We're going to look quickly on double neutron stars and neutron star black holes. Here we have a broader, bigger uncertainty on the measurement, but actually a stronger constraint that is accepted in the community. The dynamics channels are actually cannot produce double neutron star mergers at anywhere close. These are upper limits here, upper limit here. And this is a case, this is young open cluster and a single case among all the studies. They cannot produce double neutron star rates within the constraints from the measurements. So double neutron star mergers are now thought to only be coming from isolated binary evolution. And by the way, the gravitational wave measurements are very much consistent with short gamma ray burst constraints, kilonovae constraints, and galactic pulsar binaries. These are empirical rates. And last but not least, we have neutron star black holes now. The rate is, of course, a little broad as well. But again, neutron star black holes are not formed easily within dense clusters. And we think that the majority dominant channel is isolated binary evolution. So, so this is the summary with our rate situation. And I will go back, I will transition now to discussing masses. Any constraint, any question on the rates? Okay. So now we're gonna look at the mass distribution, and remember, we're looking to understand, yes?
Being tardy to the party here, yes.
This is almost certainly a really dumb question. How do you have like non-integer numbers of detections?
Okay, so I heard, how do you calculate one?
Non-integer numbers of detections, like the 2.85 and the 3.
Yes, okay, yeah, that is just, I do it on purpose because I wonder if somebody will ask the question. So we had a source early on, which based on our statistics was deemed to have a probability of being astrophysical and not noise of 85%. So that's where the 0.85 comes from. With more and more data, that source actually has now risen to be an astrophysical source. Okay.
Oh, thank you.
Okay. All right. So this is our latest results on the mass distribution, underlying corrected for selection effects, mass distribution of black holes. And I'm showing you here, the blue are the latest results. And this is done as we're looking at the rate density. So per gigaparsec cubic, rate per unit time. And it's a mass distribution, okay? So as a function of mass of any of the black holes. Okay, this is not just the it's any of the two black holes. We're not looking at the product of the mergers. And it is in good agreement with what we had extracted from the previous catalog. So number 3 is the catalog now with all 75 well-trusted binary black holes. So we have consistency. And the thing to notice is that there is a couple of possible features here, that maybe we have a bump or an overdensity or whatever you want to call it at around 10 solar masses, and maybe a bump and overdensity, etc., at around 35 to 40 solar masses. So we'd like to understand, and then I'll talk a little bit about the low end, but we'd like to understand, well, first of all, are these real? So I'll make a couple of comments there from the data. And then if they are real, what do they mean astrophysically? So statistically speaking right now, we can say that we've seen this bump we have seen now persisting through our increasing sample for a while. So we consider this to be real. What we can't say it's real is whether it's a true bump, so a rise here, or more of a cutoff, you know, a drop with a change like a flatness and a drop. It looks like a bump here, but this particular model is basically 2 power laws and a Gaussian added, okay? So we are not claiming necessarily that this is a true overdensity here, but it is a feature. And then for the 10 solar mass also, we think there is a feature, but the overdensity here might be potentially an artifact that has to do with the fact that we are here including the neutron star distribution and the fact, even we remove the neutron star distribution, we still have this bump, but at these low masses, we have very strong selection effects. So our sample is not highly dominated by low mass black holes. So it's possible that this is still not as robust as we would like it to be. And notice my language. In the collaboration, we are very, very conservative in what we claim, okay? All right, so I'm gonna come back to the astrophysics, but let me stick with the data. We also look at the low mass regime, and not to, there's 3 different colors here because we try non-parametric fit or a parametric fit, etc. And the only robust statement we're making is that there is a drop between 2 and 3 solar masses that we think is robust based on all the statistics described in the paper. But we don't see a gap. And there is a gap between 2 and 3, between 3 and 5 solar masses, definitely in electromagnetic observations, which we don't see in the gravitational observations right now. What we do see is this drop, significant drop from 2 to 3, indicating that the neutron star mass function and the black hole mass function, where the distinguishment happens between 2 and 3 solar masses, must be of different origin. So confirming our overall understanding that it's not a smooth transition from neutron stars to black hole mass function, okay? So going back to the high end, there is no good model right now to explain the feature at 10 solar masses. And that's all I'm gonna say. And I don't mean from the collaboration, I mean from the broader literature, okay? For the 40 solar mass, there is a broadly discussed, rather well understood possibility that that drop at around 40, 35 solar masses quite possibly is connected to a mass gap that was predicted decades ago associated to pair instability supernovae, where basically in very massive stars, you end up with effective pair production when they become really hot at the end of their evolution. And they end up experiencing a supernovae that drives a thermonuclear explosion in the centers and does not leave a remnant, does not form a black hole and destroys the whole star. That means that you have a gap in your black hole mass distribution. Before that gap, you have a range also, you also have pulsational pair instability effects, where because of the pair instability formation, you actually drive sudden wind mass loss episodes from the star. You have huge mass loss from the star, and right before the complete disruption of the star in the mass regime of the progenitors, you end up making your progenitors all lose mass very effectively at the very end of their life. And therefore, you're taking a wide range of progenitor masses and forming lots of black hole masses all around 35 or 40 solar masses. Now, I just said 35 or 40 solar masses driven by our observations. If you look at the theory, this pileup of black holes, because of pulsational pair instability, theoretically is predicted to be potentially up to 50 solar masses. And I'll come back to this statement. The gap could be all the way up to 120 solar masses, depending on the stellar astrophysics and the physics of the pair instability supernovae. So I won't describe this plot in detail, other than to say this gap is more prominent and forms at low metallicity and not so much at solar metallicity. Now, this lower edge of the gap, is it 50? Is it 35, 40? Is it 60? Some people will argue it's all the way to 70, 80. It's very sensitive to a number of things we don't understand about stars. Nuclear reaction rates of this particular nuclear reaction, convection treatment, treatment of radiative transfer in the hydrogen envelope, stellar rotation, and even stellar collisions that can happen in the dense stellar environments. So we can't really theoretically say where might we expect either a concentration of black holes and then a drop or a bump. Our data show a feature at 35 to 40 solar masses. That's what we can say. And then the next question is, but if you look at our data, it's not like you have a pileup and then a gap. You have some, low rate, but a real rate of detections and actually individual systems that we measure clearly that contaminate this potential upper mass gap. So then we ask the question, can this mass gap be contaminated? Well, one possibility is that it can be contaminated by stellar rotation. Different stars have different rotations, so you can get different pileups at different masses. Or you can have it contaminated through dynamical processes, a contribution of binary black hole formation from dynamical channels. And therefore, through the stellar collisions, you can actually avoid the pair instability to happen. And therefore, you can form more massive black holes. Or you can contaminate it through hierarchical black hole mergers that can happen in dense stellar environments. What do we mean with that? We don't mean stellar collisions. We mean you have black holes in clusters, globular clusters, nuclear star clusters, or AGN disks. They are merging. They're forming what we call a second generation black hole. And that second generation black hole does not escape your dense stellar environment. Stays in your dense stellar environment and has the chance of merging with another black hole, another first generation black hole, or actually another second generation black hole, and form a hierarchical merger. That's what we mean with hierarchical mergers. So I can tell you that this question has been asked by many groups, including my group as well. And I'll tell you the punchline result of one of my students, and I can see that I'm running out of time rapidly. And I'll just tell you without actually explaining the analysis that in this context of hierarchical mergers, we can show statistically that there are at least two systems in our sample, these two systems with their phone numbers, that with the current catalog have a high probability, high Bayes factor, actually high odds factor, that they come from hierarchical mergers. And I will leave it at that. I will skip a discussion of low mass gap because I am running out of time, and I would like to transition to some spin discussion. As I said, any questions on the masses for now?
Yes,
I do not know, can I be heard?
I can repeat it. if
Okay,
you
you can
can.
repeat the question. I think you had it on one plot, but maybe you can very briefly comment on it. The mass gap, how metallicity?
How metallicity dependent is the mass gap?
How much what dependent is the mass gap?
How metallicity dependent is the mass gap?
Oh, metallicity dependent. Yes, metallicity can play a role. And it is, I had it in the plot, yes. I was gonna go by memory. So let's see here. So this is roughly, this curve is solar metallicity. So you see there's a drop, but we don't have a gap actually. This is compact object mass as a function of ZAMS. The true gap starts appearing according to this set of stellar models, you know, one convection assumption, no rotation, etc. The gap starts appearing at a 20th of solar metallicity and lower solar metallicity. Okay.
Thanks.
Thank you.
Okay. So a few comments on spins. The spin situation is a lot murkier. The literature is very confusing. In fact, I was in Aspen in January, my first in-person conference, and one of our colleagues, collaborator of mine, past postdoc of mine, Will Farr, gave a talk with the title of how I can't remember exactly, but basically how, let me confuse you about spins, okay? We are all confused, the experts, and we're not sure what to make of the spin constraints and the theoretical expectations about spin. So expect to be confused. In fact, right after I give this talk, I have a 6-hour workshop with my group alone to try and make some sense out of our current understanding of spins and how to maybe crystallize a few ideas. But let me tell you a few things that I think we can all agree. First, we don't measure spin, individual black hole spins directly. That's part of the problem. What we measure is what some of you may have heard, it's the chi effective. This graphic tells you what the chi effective is. And this formula tells you even better. It's a mass-weighted combination of the aligned components of both black hole spins. Aligned with what? Aligned with the orbital angular momentum axis. Now you might say, why is this useful? Before I get there, let me tell you why this is the only thing we can measure. It's because when you account for spin orbit and spin effects in the waveform, this is the quantity that dominates and controls amplitude and phase modulation of the gravitational wave signal. So that's what we can constrain or measure. Now, why is this useful to some extent? It's because based on our two formation channels, isolated binary evolution and dynamics, it is the difference in spin alignment that maybe will be useful and allow us to distinguish between formation channels. Easiest to explain, dynamics. In dynamical settings, you form each black hole independently. Each black hole has its own spin magnitude, and when they come in a binary through dynamical process and eventually merge, there is no reason that the spins have anything to know about one another. So they can be oriented isotropically. Okay, that's the expectation. So if spins are isotropically oriented, then chi effective has to be symmetric. The distribution of a population, purely dynamical population, that chi effective distribution has to be centered at 0. That's a strong expectation. If you're forming most of the binary black holes through isolated binary evolution, with some caveats that I'm not going to explain in detail, the expectation is that chi effective has to be always positive, like it's very hard to anti-align in isolated binary evolution, and it has to be positive but relatively small, like the spins are mostly aligned with the orbital angular momentum because of the prior binary evolution. Okay, so these are the two big thoughts, let's say. All right, what do the data show? Well, this is our chi effective distribution. Bluish is the here. Don't get me started of how inconsistent our plots are from our papers, but blue here is the old catalog and black is the new catalog. What you can see is that both catalogs are consistent, basically. More discoveries have not changed the punchline. Well, it's very clear we can exclude at high confidence that our chi effective distribution is not centered at 0. So we argue that we probably have a mixed population. Why mixed? Because it's not centered at 0, but it's not all on the positive side either. So the small negative contribution would imply that we have some contribution of anti-alignment, but not a big one and not dominant. Otherwise, we should be centered at 0, and we're not. So mainly isolated binaries with a small fraction of dynamically formed mergers. You'd think this is simple. Great, we have a nice conclusion. Well, it's not that simple. We are fitting our data with a Gaussian. If we had a distribution that was actually supposed to be all positive, but favoring small chi effectives, so close to alignment, and you try to fit it with a Gaussian, then the way you're fitting it may give you a small negative tail. So there's a lot of work out there that argues this is an artifact. So maybe there is no small fraction of dynamically formed mergers. So that's one point, a few points that I will make for how it's not simple. You might say, why are you fitting with a Gaussian? Abandon the Gaussian, do something else. Well, yes, I can tell you we've done things both in the collaboration, in my group, outside the collaboration, and many other groups. And basically whatever you choose to do, let's say a delta function at 0 or another distribution that just high rises all the way to 0, there's always some kind of a statistical bias, and the sample is still too small. And because our measurements on chi effective still have big error bars, that we cannot make a strong statement yet. And that's the punchline. I'm gonna, looking at my time, there's results that go into more nuances of these issues, comparison with high mass X-ray binaries and the spin measurements there, completely different methods. High mass X-ray binaries are supposed to be progenitors of binary black holes. Very different picture there. Why? There's a lot of mysteries there that I'm afraid it's not possible to cover. We have a graduate student of mine is bringing forward a possible explanation for the discrepancy between high spinning black holes in high mass X-ray binaries and low spinning black holes in binary black holes, but it's no proof. It's a potential hypothesis. So with a lot of skipping, I went through 3 of my topics. Maybe I can spend 1 minute on each surprise I was going to mention. As I said, we have 2 double neutron stars. One, the multi-messenger source. You've heard, I'm sure, tons about that. I won't say anything. It's actually not that much of a surprise. The second double neutron star is a surprise. And it is a surprise in terms of the neutron star masses. The punchline is this plot where we're showing total mass. The distribution of galactic binaries is here in terms of total mass, well-measured masses, remember, in radio pulsars. And they're here, well below 3 solar masses. This one system, whatever you assume about the spins of the neutron stars, total mass clearly off scale. We have discovered a population of tight neutron star binaries. They're merging, and the neutron star masses are off scale. We don't understand how is this possible. The rate calculation is high. It's comparable to the radio pulsar population in our galaxy. Where is that population? Why are we not seeing them as radio pulsars? So that's a big question. The next oddity is this system you may have heard about that has the most extreme mass ratio down to 10⁻⁴. The black hole mass, 23 solar masses, and the low mass object mass, very well constrained, very unusually well constrained, 2.6 plus or minus 0.1 solar masses. High signal to noise ratio, long signal because of the low mass ratio, well measured. We don't know what this object is. Is it a very massive neutron star or a very low mass black hole? Either way is a record breaker, but we can't tell. And the inferred merger rate from this one source, remember what I said about trusting merger rates from one source, is high, relatively high, not very high, but high for all astrophysical models. No model right now can produce mass ratios of 0.1 at this rate. So we can't explain this system or the implied population of this system. I'll skip and just leave you with the fact that with all these discoveries, we're very busy and excited, but we are doing a lot of work planning for 3rd generation detectors, Cosmic Explorer and Einstein Telescope. And we're looking forward to many decades of gravitational wave astrophysics. Thank you. And I'm sorry,